Hello, and welcome back to Unit 3 of our course on thermodynamics. So in the previous lessons, we have discussed about what is a thermodynamic system, what is a thermodynamic process, and we have uh, uh, known how to quantify the work done in volume changes at constant pressure. So in this lesson, we will be now talking about how does the path between thermodynamic processes or the path between two thermodynamic states affect the heat and the work done by or on the system. So let's start with the work done by or on the thermodynamic system during a change in state or during a thermodynamic process. So the work actually depends on the path between these two states. So here we have states 1 to 2. And as you can see here, in going from state 1 to 2, there will be 3 paths. You can either follow the path 1, 3, 2, or you can follow the path 1, 4, 2, or this curved path here directly from 1 to 2. And each of these 3 paths will have different amounts of work done on or by the system. So first, let's consider the path 132. So in the path 132, you first start with the change in state or the thermodynamic process 1 to 3, wherein the pressure is at P1 and the volume changes from V1 to V2, which is at point 3. So in that case, the work done in the process 1 to 3 is just P1 times the change in volume, V2 minus V1. Now, uh, after the process 1 to 3, you then go to the process 3 to 2. So in this case, the volume is constant at V2 and the pressure drops from initially at point 3, the pressure is P1 and it now goes to point 2, which the pressure is P2. So in that case, the work done in 3 to is 0 because there's no change in volume. Again, if there's no change in volume, there's no work done on or by the system. So the total work done in this case is just purely due to the process 1 to 3 in this case. And the work done is just the area, this orange shaded area here. So the area of that square. So the length of the square again is P1 and the width of the square is this width here is V2 minus V1. Okay, the second path is the path 1, 4, 2. So in the first case, or in the first segment of the path, you have segment or path 1 to 4. In path 1 to 4, this is at constant volume V1. You just decrease the pressure. And in that path, there's no work done because there's no change in volume. The volume is constant. The work done is actually just here in the path 4 to 2. It's the area under this curve here. So the work done in 4 to 2 is just the width of this triangle or the height of this triangle, which is P2. And the width of this triangle is V2 minus V1. So it's just the area of this triangle here. But you will notice that the total work done is just this work here, the work from 4 to 2, but it's still less than. It's not the same work as compared to the previous case in the 132 case. Because in the 132 process, the work done is this whole rectangle here. In the process 142, the work done is much smaller or much lower. So again, the path between thermodynamic processes affects the work. So it depending on the path, the work may increase or decrease, or the work may be larger, or the work may be lesser. So lastly, in the direct na path, the direct curve path from 1 to 2, path number 3, you increase the volume here, you expand the volume from V1 to V2 while decreasing the pressure from P1 to P2. And the work done here is actually this area, again, the area under this curve. And it's actually much lesser as compared to the work done in the process 132, but it's greater than the work done in the process 142, because in the process 142, the area is just this small triangle here, or the work done is equivalent to the area of this small triangle here. So again, different paths, the paths 132, the paths 1, 2, and the paths 142 all have different work done or by the system involved. So the work, again, in thermodynamic process depends on the path. It doesn't have, it doesn't always have the same formula. So we will discuss actually more about the different types of thermodynamic processes in the next lessons. So the same with work, the heat in thermodynamic process also depends on the path between the initial and final state. So in this example, we have a hot plate and we have a gas, and there's a movable piston here. So meaning the volume of the gas is allowed to change. So the hot plate uh, gives heat into the gas. So the gas absorbs heat, which makes its volume change from 2 liters to 5 liters. But its temperature remains at 300 Kelvin. So in this case, there's work done because there's a volume change. So the work done by the gas is positive, and the heat absorbed by the gas is also positive because it's or the heat is positive because heat is absorbed by the gas. So in this case, both the work and the heat are positive. In this another example, we have some sort of a pressure cooker na scenario wherein the volume of the gas of the container is fixed. In this case, you have and the whole thing, the gas is insulated. The gas is initially in this side of the partition, so there's a breakable partition, and the gas is at 300 Kelvin. And in the other side of the partition is just vacuum, so nothing. Vacuum means nothing. There's nothing there. There's no particles there. There's no air there. It's vacuum. Now, when the partition expands, even though uh, uh, even though the partition expands or the gas expands in this case, but there's no change in volume of the whole thermodynamic system. So there's no change in volume, meaning there's no work, and the system also doesn't absorb or releases any heat, so the heat is zero. Q is zero. So this is an example of an thermally isolated system. So I think we have mentioned about thermally isolated system before in the unit number 1, such as the calorimeter. So if you have a calorimeter, an isolated system, heat cannot enter or leave the system. Okay, so that is the end of this lesson. So we are now uh, getting very near in the uh, main topic of this unit, which is on the first law of thermodynamics. So I will see you again in the next lesson.